So there are a number of different types of measurement that you might want to take. These include number or counting, intensity, shape, distance and other spatial analysis, colocalization or co-occurrence, and tracking. These are the standard categories, and I will discuss them in more detail in the following slides, but there are obviously other measurements that you might want to make. One of the most common measurements that you'll want to make is counting. So this can be in 2D or 3D or over time. The ability to automatically detect and count objects is powerful because it means that you don't have to do this manually. And in many cases, we need to count the number of objects per a specific container. And a container could be a cell, region of interest, or a volume. This allows you to present the counted object as a function of a single container, for example, the number of cells in a measured area, or the number of cells in a region of interest. One measurement that you'll often need to make in fluorescent images is intensity. So if we wanted to compare the brightness between these two images, one way that we could do it is to measure the mean intensity of each nuclei and then compare them. So the mean intensity is the sum of all intensity divided by the area measured. So let's say we measure the mean intensity of each nuclei in these two images and we plot them so that we're comparing the control against the treated population. And what we see is that the treated population has a much higher intensity and has two distinct populations. Apart from measuring the mean value, we can also measure other intensity features such as the minimum, maximum, median, and sum intensity, and the standard deviation, which can be used to quantify other features. In this example, we have two objects that have a similar mean intensity, but we can see that there is a clear difference in the distribution of fluorescence. The cell on the left is smooth, but the one on the right is more granular. If you look at the histogram of each cell, you can see the range of intensity distribution is spread over a greater range on the right, and we can measure such dispersions using the coefficient of variation, which is the ratio of standard deviation to mean intensity. So this measurement can be used to determine the degree of fragmentation or homogeneity in an image. The next common measurement I'm going to talk about is shape. There is a wide variety of morphological measurements you can make when analysing biological structures, but the most common ones are area in 2D, or volume in 3D, or perimeter in 2D and surface area in 3D. In this published example, these two parameters were used to describe the morphology of an object in 3D images using Amaris. So during glial ramification, the processes of the cells grow longer, and this increased length influences the surface area more than it does the volume. So the increased ratio of surface area to volume is an indicator of this morphological change. Another useful shape measurement is convex hull, which measures the minimal polyhedron that covers an object. So one way of visualizing how this works is to imagine an elastic band which has been placed around the outside of the object. A convex hull can be fitted in 2D or 3D and measures the spread of an object. Similarly to the area to volume ratio measurement that was shown in the previous slide, we can also measure how solid or complex a shape is using the ratio of area to convex hull or perimeter to convex hull. If we want to know more about the size of an object, we can measure the minimum bounding rectangle around an object, where we can get the longest side of the rectangle, and you can also use this to measure the aspect ratio, which, as we discussed earlier, is a good indicator of roundness. Or we can measure the Ferret diameter, which will be the longest possible line that can be drawn in that object. And finally, we can look at the angle of an object if direction is important to your analysis. Naturally, when we measure roundness in 3D, we can also measure some other shape descriptors such as sphericity or elongation. If you are working with neurons, it's almost certain that you will need some form of filament analysis. Here I've shown an example of 3D filament analysis done in Amaris. but this can also be done in 2D. When an object is processed as a filament, it can be further classified as branch or spine, and we can also measure branch level, length, or angle. And in this picture, the filaments are color-coded based on the branching level. Or we can do shoal analysis, which counts the number of branches per concentric shell. And in this image, the branching points are color-coded based on the concentric shell in which they belong. Sometimes users want to measure the distance between objects. If we want to measure neighbor relationships, we can measure the nearest neighbor distance, which is the distance between the centroid of one object to another. And this works well when features are small compared to the distance between them, or objects are small, round, and regular in shape. If objects are large compared to the distance, irregular in shape, or vary in size and orientation, it may be more appropriate to measure the distance between the edge to edge rather than a centroid. And this is done using the minimum separation distance. Here is an example where we want to identify the particles that are touching this cell. However, the shape is quite complex, so the best way to measure this is to measure the minimum separation distance between the edge of the cell and edge of the particles. We can do this by first creating a Euclidean distance map outside the cells by increasing the pixel intensity from the border of the cell outwards. Then we can measure the intensity of the particles on the distance map, where the particles with a minimum intensity of 0 are classified as touching the object. When it comes to measuring the close contact between objects, one of the most common methods used is colocalization. Colocalization gives a general indication that two fluorophores are near each other, but it doesn't say that they are interacting or that they are in the same location. When we measure colocalization, we can measure if there is a relationship between two channels using the Pearson's coefficient, or we can measure if they are generally near each other using something like the Manders coefficient. Finally, we can also determine if they are overlapping in the 2D area or in a 3D volume. As you can see in this example, colocalization is highly dependent on the resolution of the acquisition system. In lower resolution images, you'll find a much higher level of colocalization, and this will give you a false positive. So we need to be careful with planning when we want to measure colocalization, which is why we have a specific workshop on this topic in June using Fiji and Imaris. Finally, we have tracking, where we can use live cell imaging to create a time lapse and track object movement. Some of the things that you can measure are speed, displacement, direction, accumulated distance, straightness, or how long an object has been traveling for. If we were looking at total mobility, displacement would be a good measurement to plot. And in this example, we have shown that the treatment has caused a reduction in cell movement. Or if our interest is in cell development, we can look at cell division and track lineage using tools in Fiji and Imaris.